Data types, part 1 of 2. In this nugget, we're going to introduce a fundamental construct in the Python language, and that is how data structures are represented. We're going to start at the very beginning, ground floor, and I'll gradually increase the level of complexity as we go on through this nugget and then the rest of the series. After we introduce what data types are and how they work and some relevant vocabulary, we'll begin our consideration of specific data types in Python by first examining numbers and then strings. Let's get to work. Of course, in learning any technology, there's relevant vocabulary that needs to be picked up. First, I'd like to show you this. This is a bulleted list that gives us the general, high-level Python program flow. And I think this flow is useful for many reasons. It gives us a larger picture of Python program execution and also enables us to define some very appropriate vocab words. A Python program is going to be one or more files that have the py extension that accomplish some goal or set of goals set forth by the developer. A Python program, as I said, could consist of a single top-level file, or it could actually consist of several files. What happens is you can call or import external .py files as what are called modules. Technically, the vocabulary can get a little bit overly flexible in Python as compared to some other languages like Java and C, because actually a module, really, strictly speaking, is any Python script file. But your top-level file, as I said, might have need to access functions that deal with higher-order mathematics, trigonometry, scientific constructs, and this kind of stuff. And rather than reinvent the wheel and create those functions in your top-level program file, why not import a .py file as an external module? Okay, so the top level of Python program flow is that your Python program consists of one or more modules. This is going to be your top level .py file, and possibly in addition one or more imported modules. Now you're going to find in the Python literature references to what's called the standard library. Some folks like to say that Python is a batteries included development environment and programming language because you get a whole bucket load of core modules, these are called again the standard library, that ship with the CPython distribution and enable you right off the bat to begin to do imports to do things, for instance with numbers, like pseudo-random number generation, higher order math, etc. So that's enough for now about that. At the module level, once we drill into a specific .py script file, we're going to find that those files are composed of statements. Statements can also be looked at as reserved keywords. In a future nugget, we're going to look at all of the Python built-in reserved statements. The statement in Python is some reserved word that calls some specific action to play. Within your statements, you're going to find expressions. An expression is primarily a mathematical or computer science term that deals with performing some kind of operation on data values and winding up at the end of the expression with a single result. I always sometimes think of as a coffee bean grinder where you pour the beans into the hopper, turn the crank, and you wind up with the powdered coffee ready for brewing. Similarly, if you perform, let's say, an addition expression, you're going to take one data value, add it to another data value, and then wind up with a result. Finally, expressions generate those results because they perform work on objects. We're going to formally define what an object is momentarily. For now, just consider an object to be the fundamental building block of a Python program, and really anything can be an object in Python. Python is very forgiving and has a very relaxed syntax and grammar as a programming language. Speaking of objects, let's now define objects and types in Python. As I said, just about any data structure or any entity is considered an object in Python. An object is, I guess, formally defined as a data entity that either does or does not have associated attributes, methods, functionality, etc. Some of these terms, like attribute and method, we're going to hold off on a little bit, but just suffice it to say that an entity can be a class, a function, a name or a variable, etc. Anything you operate on or use or call or define in Python is considered an object. Now the next thing, and this is a pretty key point, Python is both dynamically typed and strongly typed. Now what does that mean? You'll often see references to typing when programming languages are discussed, and we're not talking about Mavis Beacon teaches typing. We're talking about how data is represented. In other words, are we talking about numerical data? Are we talking about character data, also known as string data, etc.? What are the rules that the programming language puts behind characterizing different types of data? Now, the deal with dynamic typing as opposed to strict typing is that in Python, you do not have to, when you declare, say, a variable, you don't have to specify the data type that it is. Like, let's say we were going to define a variable named t that was going to store date-time information. We don't have to declare that in our code as t and then make some kind of data type association like we do in many programming languages. Certainly C#, certainly Java are very strictly typed languages. The way it works in Python is actually really mellow. For instance, if we were going to work with numbers to perform addition or subtraction or whatever, we might have one variable called n and another one called t, and when we initialize that variable or give it an initial value, depending upon what we put after that variable or that name is going to be the data type that Python associates with it. So in this case, a 1 and a 2 are going to come back as integer data types. If we create a variable named s and we give it some kind of alphanumeric or character string, well, you know that that's going to come back as a string data type. Some old school programmers find the dynamic typing in Python frustrating. They want more rules, but we have to remember that Python was developed to be as easy to use as possible. Now, whereas Python is dynamically typed, it's also strongly typed. In other words, there are rules governing what's called mutability. With numbers and string data in particular, once you define a variable or a name, those are pretty much synonymous terms, by the way. And actually, why don't I take one step back and quickly define what a variable is? We're certainly going to be using them a lot in this nugget and each and every one of the following ones. A variable, the word variable outside of computing, you know, means non-static. Therefore, a variable is some representation of data that can have its value changed over time. Finally, the formal definition of a data type is a data classification with certain characteristics. That is to say, at first blush you might think Python could only add, subtract, multiply, or divide numbers, but that's only partially true. We can actually use the plus sign to perform what's called concatenation, where we combine non-numeric data. And you're going to see that in an example very, very shortly. I want to jump out into the Python shell here really quickly to elucidate this notion of dynamic typing and strong typing a little bit more. Rather than how I traditionally do nuggets, where I'll do a series of whiteboards and then a dedicated demo, I think that this course is much more effective in a workshop format in which we just ping-pong directly back and forth between the slides in our shell. And some of the things I'm going to be doing here we're going to cover formally and in great detail in this nugget and upcoming ones. So I want you to take a lot of what I'm doing at face value and just try to understand the flow. So I'm going to start by defining a name or a variable. Remember, those are synonymous terms in Python, and we'll call it 2, and I'll call name B Tim. You can call a built-in type function, and you notice that as soon as I use the word type and then open the parentheses, this is one of the nice things about an integrated development environment. Python gives us some help or some suggestions on how to use this function. And what we can do is simply pass in the name or the variable that we built. And now I'll do it for B. And Python interpreter will come back with us with the data type that it dynamically gave to that object. Remember, the purpose of these variables is to make your code modular. Imagine hard coding Tim and 2 throughout your application, whatever your application did. Then what if you wanted to change Tim to Sue, or if you wanted to change 2 to 4? It's not going to work. So variables or names represent a way to abstract that idea. Let's do one more example of dynamic typing. I'll define a variable C as 3.14. And then when we pass c into the type function, it tells us it's a floating point number. We have an integer or a solid straight ahead number with no decimal point. We have an example of a string or just character data, and then we have an example of a floating point decimal called, you guessed it, float. Now, as far as the strong typing goes, I'm going to leave mutability and immutability alone for now. The other main definition of strong typing is where Python will prevent mixing operations between mismatched types. Now, what the heck do I mean by that? I'm going to demo this by creating a function. A function in any programming language is a subset of a larger program that defines some modular unit of code or performs some specific action that returns and acts independently of the rest of your program. I'm going to create a very, very simple function called adder. And the way, again, to use variables, or one way of many to use variables and to create that level of abstraction, is that I'm going to create this function called adder that will add any two numbers that are thrown at it. I'm going to define them as, let's say, x and y this time. Use a colon, and notice that the indentation takes us in. We're going to understand the purpose of indentation pretty shortly. And all I'm going to have this do is print back the sum of x and y. That's all the adder function is going to do. But the neat thing about the xy here after the adder, this is what's called the argument portion of the function, is that now when we call or run the function, which I can do just by typing adder, we can then pass in whatever arguments we want. So I could say 2, 2. Comes back with 4. What happens is those two input parameters get bound to the x and y variables that I created in the function's definition, and sure enough, dynamic typing is going to map these 2's to ints. Now, what would happen if we called adder like this? Is that going to work? I think you're getting a theme here that whenever we want to do a literal string or character data, we would pass in either single or double quotes. I'm using single quotes here in this example, but we could actually use double quotes too. If you have experience with other programming languages, you might wonder if Python is going to perform a dynamic type conversion where it will take this 2, even though it's defined as a string here going into the function, and convert it into an integer. Let's see. Nope. When you error out in the interactive shell, you'll get what's called a traceback, and it'll give you some really rich detail as far as where your error goes. You can even right-click in one of the traceback areas and choose Go to File Line. Of course, it's not going to work here because I'm not working with a separate py file. I'm working in the shell. But regardless, traceback tells us down at the bottom in the specific error, unsupported operand types for plus, int, and string. So that's an example of strong typing. We can dynamically have Python associate data types with variables, but we do want to be careful on how we're using them in context. On the other hand, we could certainly take two strings, like I'll say Tim plus Warner, and put those together. This is what's called concatenation. But yet again, if I try to mix a string with an integer, by default, Python's going to choke. Now let's have a look at the core data types in Python. You see that there are fewer data types defined, especially for number, where there's just really only 2. As we saw in the previous example, there's integer and float. Now that's true for Python 3.x. Python 2.6 actually breaks integer out into 2 subcategories. But because we're focusing on Python 3, our core data types are number, string, and tuple. Those are the immutable data types. In other words, once you define a name or a variable using that data type, it's going to be that data type and that value forever. Now you can create a new object, like let's say for instance we had a variable called 3.14. Now what data type is that going to be by default? Well, you know that's going to be a float, don't you? We could do something like this, int a, and what that would do is essentially just take this .14 and chop it off and come back with a value of 3. But we wouldn't be able to say a equals int a. We would have to create another variable that takes this 3.14 float, just essentially chops off the right of the decimal point, gives us our 3 integer, and then we have our original a that's a float, and then we have a b that's an integer. integer, you see? Works the same way with strings and tuples. Now, we haven't talked about tuples yet or any of the rest of these. We'll get to those later. But immutability, think about it, is once you define a name or a variable, it's going to be that forever, unless you just blow it away and create another one with the same name. Mutable data types are your lists, dictionaries, and then operations on files. Lists and dictionaries are multi-element data structures, whereas so far we've been defining A equals 1, B equals CBT nuggets. A list is a way to take multiple elements, which could be of many different data types, and keep them all associated with the same variable. It's pretty handy indeed. In fact, crucial in many Python programs. Dictionary is the same idea, but it puts together what are called key and value pairs. More on that later. And certainly we can dig in, create files, edit files, delete files, print files, email files, FTP files. Well, you get the idea. We can operate on files. All right, let's drill into numbers now, and then we'll do some more demo stuff. As I said, in Python 3, the Python Software Foundation has stripped things down a little bit. Dynamic typing means when you create a value or a name that does or does not include a decimal point, you're going to wind up associating with either the integer or the float data type. Python 2 breaks out integers into long varieties, but in Python 3 it's just a straight ahead integer. An integer is a number without a decimal point. 0, 1, 2. Float does include degrees of precision, 3.14, whatever pi is, if you know that. Both of these number data types, integer and float, are signed. In other words, we can create a value of positive 2 or minus 2, positive 3.14, minus 3.14, etc. And as we saw, there's a useful function in Python called type that we can use to verify the data type for any name. Some other ones that are interesting are isInstance. IsInstance is a function that we can use to test for a particular data type. The question here is, we have a variable, let's say, called v1. We can run isInstance against it to find out whether v1 is being classified as a float or an integer. Sometimes it's not as obvious as you might think. You can also perform type conversions. Remember that numbers are non-changeable or immutable, so what you're doing when you run the int or the float function is that you're taking the float or int respectively, or possibly even a string that you pass into these functions, and you're winding up with a separate name of that destination data type. I'll show you what that looks like in just a second. Remember that expressions involve, generally speaking, at least two operands, or objects that are being operated on. An expression must have also at least one operator to perform actions upon those operands. You have your traditional arithmetic symbols like addition is plus, subtraction is minus, multiplication is the asterisk or star, simple division is the /, double / is integer division, where you're not going to wind up with a remainder. The percent sign is what's called the modulo, that performs a division that gives you only the remainder back. Exponentiation, 2 to the power of y, let's say, is done by double star. Then we can do various comparisons, less than, greater than. Notice that the equal comparison is double equal. There's an important difference in any programming language, certainly Python is among them, the difference between a single equals and a double equals. Now, a single equals is what's called an assignment operator in a programming language. We use equal to tag data. So when we've been doing A equals 1, B equals CBT nuggets, we're using the assignment operator here, the single equal sign, to associate a name with a piece of data. Now, if we're doing tests, like let's say we're creating a simple number guessing game, and we want to evaluate whether the number that the user's giving us is less than or greater than the number that was generated by the program, well, that's easy enough. How do we determine if the number given by the user matches exactly the number that was generated by the Python program? Well, here we use the double equals. Double equals is our equality operator. Keep that in mind. Now, to every equality operator, there's an inequality operator to specify not equal to. The shorthand for this is what's called bang equals. Programmers speak for the exclamation point is traditionally given as bang. So exclamation point equals evaluates to not equal to. All right? And then finally we have the Boolean comparisons, and, or not. Finally, we have to please excuse my dear Aunt Sally. This is something I learned when I first got into computing many years ago, is a shorthand mnemonic for remembering the order of operations. So far, I think you've gotten the idea that Python's a friendly language and all of that good stuff, but we still need to keep in mind clarity when we're doing mathematics. Parentheses, exponentiation, multiplication, division, addition, and subtraction. This is the order of operations when you're doing math. Note that parentheses is evaluated first. So in my experience, and what I pass along to you, is make liberal use of parentheses when you're gathering data to do number crunching, because those blocks will be evaluated first, and then, as I said, exponentiation, multiplication, division, in that order. Doing simple math and simple arithmetic is fine until somebody puts an eye out. Just kidding. However, Python, as we've discussed in the introductory nugget, is very well suited for higher order mathematics. Therefore, Python you'll see in the science and math and higher educations and research milieus as well. The standard library gives us two modules that we can import and use. Fractions is optimized for, you guessed it, fractions. Math allows us to do higher math that's inaccessible just directly baked into the interpreter. We can do import math to do things like trigonometry, basically. That's something that comes to mind easily, sine, cosine, tangent, etc. Then outside the standard library, but certainly easy to find on the web, download and install, the two more popular, if not most popular, complex math modules for Python are NumPy and SciPy. These are heavily used in industry and in education. The first thing many folks do with Python when they're just getting their sea legs, so to speak, is to use the Python interpreter as a glorified calculator. Now notice that we don't have to create names for everything. We can just run straight expressions here and evaluate them, run them against the interpreter and see what happens. Remember that your integers and floats, etc. are signed, so 3 minus 10, of course, yields -7. We can do our multiplication, division, and that's an interesting point actually. Let me do that again, but this time get a name back. You'll note that when we perform division, we're getting floats back. That's especially advantageous, of course, if we do something like this. Remember isInstance? We can pass in a name here. If you don't give enough syntax, of course, you get a traceback. Tells us that isInstance expected 2 arguments, got 1. That brings up a good point, actually. Online help in Python is rich and robust. If you're calling a function, either a user-defined function that you wrote or one from a library, you can run the help function and simply pass in the name of the object that you need help with. Of course, you have to spell it correctly. And the online help will come back with whatever metadata or documentation string is associated with that function. So in this case, I'm going to test to see if my division name is an int. That comes back Boolean false. Now, this is a neat trick. If I want to rerun isInstance, watch this. I can either mouse up or arrow up, hit enter to get my last line back. Now let me test for float. That comes back as true. Well expected. Now, to get back or echo the name of a name or the value of a name, you can just type its name. So we know that division is 10. What if we wanted to convert 10, which we know is a float, to an integer? Well, if we run the int function, we get back 10. How about if we do division equals int division? What we're doing here, we have to remember, is not changing the value of our float, which is immutable. We're literally overwriting the old instance of division. That's why using this function, or this expression I should say, division equals int division, redefines the division name. If you wanted to keep the division the way it originally was, then we should have created another name, like maybe div2 equals int division, and then we can echo that back. Of course, we've already overwritten the previous name with a new one with the same name of the integer data type, so it's all well. What about if we created a name called CBT, gave it CBT nuggets? Of course, we know that this is a string. And now let's create another name called CBT2 and see if we can convert this to an int. Nope, this is strong typing coming into play here. However, let me create another name called numstring, give it a value of 100. Now create a new name called numconv, and then echo it back, and we're good to go. So the strong typing can only allow transitions in data type if those types are compatible. I hope that I've drilled that home sufficiently. Now let's turn our attention momentarily from numbers to strings. We're going to be using numbers and strings and lists and tuples all in combination, conjunction with each other later on. But let's get the ground floor stuff out of the way first. A string is simply an ordered sequence of single character data. Don't want to use the term in my definition, of course. Now, sequence is important. Strings are a special kind of data object that's not just looked at as a single data unit. In other words, as we're going to see, if I create a string called CBT, what I'm actually doing in Python is creating a multi-character array of data. Each of these positions is actually indexed, and you can dive into a string and access index offsets individually or in a group. That's what's called slicing a substring. We'll talk about that momentarily. Now, what is character data? This is data that's represented by what's called a character set or an encoding algorithm. One big difference between strings in Python 2 and Python 3 is that Python 2 used the much smaller character set called ASCII. This is a 128-byte character set. It certainly is fine for the English language, but if we're dealing with globalization and other languages, in particular Far East languages like Japanese and Mandarin, then we're going to need an encoding mechanism that supports much wider mapping of letters, numbers, diacritical marks, non-alphanumeric characters to data that the computer can understand, namely binary. We're not going to get too far off the track here, but in Python 3, strings are now all Unicode characters, whereas the ASCII encoding mechanism, as I said, has a pretty small range of values. 128 uses about 7 bits to do that. Unicode is, and in particular the UTF-8 implementation of Unicode, is a variable length encoding system that goes from 1 byte all the way out to 4, but it's variable in order to save yourself space in your code, in your program, in your database, wherever you're employing Unicode. So enough about that. Just know that a string is an ordered sequence of character data that relies upon an encoding mechanism. And that's actually an important point that we'll revisit later in the course. Other examples of sequence data structures include lists and tuples, which we'll define in the next nugget. Remember that strings as a sequence involves position, so left to right position of those characters is significant. String literals means just simply a string definition. In other words, I might have a name called FN, and I would give that first space name. Spaces are certainly mapped to code points in the Unicode encoding system. That's a string literal, where you're mapping a name to a fixed sequence of characters. Now you'll note here that we can use in Python either single quotation marks or double quotation marks. The deal with that is you just need to be consistent when you combine them. Depending upon the rules that govern your programming shop, you might have standardized on one or the other, but the Python interpreter doesn't care. Now, if you look at my example at the bottom of this whiteboard, if I wanted to create or print out a literal string, Tim Trainer Warner, I could wrap the string itself in single or double quotes. But if I actually wanted to quote inside that larger string, I can differentiate using the other quote type. But again, you need to be consistent. I'm going to get an error, for instance, if I try to pass in the string starting with a double quote and ending with a single quote. Finally, you can use triple quotes to do multi-line strings. I'm going to talk about documentation strings in a future nugget, so I'll leave that alone. String operations. The len function is useful. You can pass in a string to the function, and the Python interpreter will give you back the character length of that string. Plus, as we've seen, is used as an addition operator with numbers. It's used as a concatenation operator with strings. By the way, a programming term alert. Whenever you have an operator, a class, a method, some object in a programming language that has multiple functions, that has more than one function depending upon its context, you'd say that that object is overloaded. So in this case, the plus operator, or the plus symbol, is overloaded such that it does one thing, namely addition with numbers and concatenation with strings. Concatenation is a $5 word that simply means you're connecting two or more strings. Repetition? Note that we can also use the multiplication operator with strings, such that if we had defined the name S as some string and multiplied it by 5, well, we're going to get some string printed one after the other with no space. Finally, you'll remember the int and float functions. This is how you can do type casting, or changing the identity or the data type from one to another. Well, we can do that with strings as well by just passing in some name, and Python Interpreter will do its best to give you back that data as a string representation. Because Python is strongly typed, you'll have a much easier time feeding in numeric data into the string function than you will inputting alphanumeric data into the int or float functions. I hope that that makes sense to you logically. Let's pop into the interactive environment and work with strings a moment. Let's define a name called CBT and another one named nuggets. You'll notice that I'm using single quotes and double quotes interchangeably here. Let's now define a name called N1, where we start with open quotes, end with close quotes. Of course, we get a syntax error there. Let's try some repetition. N times 5. Now you might be asking to yourself, well, that looks pretty ugly. How would we do repetition and involve spaces? Well, remember that strings are immutable. We can overwrite the C string, or we can define a new one. I'll actually create a new one called CNew, and I'll actually include a space in the string definition, you see. So now if we do CNew times 5, we have some spaces. Although there's another problem here, because we may not want this space at the end of this string. Concatenation works very simply. We could say C plus N to give us our CBT nuggets. Alternatively, you can quote a blank space. Please remember, this is a common newcomer error, that a space is considered every bit as much a valid string character as an A, B, a pound sign, an exclamation point, whatever the case may be. So we could say in this case C plus, and then we're quoting a space, plus N to give us a nice formatted CBT nuggets. Now in the interactive environment, these are going nowhere. If I wanted to capture this into a name, all I would have to do is prepend it. So I could call this concat, and now I've captured that transformation into a new object. To test out the len function, tells us 11 characters. If you count up the characters, including the space now, you'll find that that's correct. And then finally, I'll create a float, convert it to a string. Now here's a good gotcha for you. Notice what happened. We defined a float as 14.4. We used the string function and passed in number. We came out with a string of 14.4, but we didn't assign this to a name, so it's just going out into the ether. When we recheck the value of number, of course it should still be 14.4, but when we run type against number, notice that type is still a float. Again, numbers and strings equals immutability. String slicing. This is a really important subject, because the bottom line is, as you create strings, sometimes you might want to evaluate, extract, or view just a portion of that string. A portion of a string value in Python is what's called a substring. And the process of digging into a string and working with its substring components is called slicing. We can do slicing in other contexts as well, with other sequence types, but for now let's focus on the string. What you're seeing here is an 11 character string, CBT nuggets, pretty easy enough. And you have to understand that because a string is a sequenced data structure, we need to map each relative position in the string to an integer value. And the way it works is the leftmost position in the string is position 0, and then moving to the right, we ascend 1, 2, 3, and so forth. You can also slice strings and evaluate them in the other direction. And here, the final character in your string is position 0. And then we work in the negative value context, -1, -2, -3, etc., until you reach the first character of the string. So for instance, if I wanted to view or extract only the n from CBT nuggets, I would reference this object. Let's say this object was given the name O. You would reference the object name and then in square brackets your substring, or your what's called an index offset. So if I wanted only the n, I could either say 0 sub 4, or I could also look at it the other way and do -6. They're equivalent. That would extract just that single letter. What's especially powerful about slicing, though, is that you can do ranges. So in this first example, what you're seeing here, actually, let's do the positive example first. If we were to do O sub 6:10, then what that's going to do is extract or latch onto, copy out the data in that string from position 6, which in this case is G, up to but not including the 10th character. So in this case, this 610 would grab GGET. Now, why would you want to grab substring data? The sky's the limit. There's tons of reasons. The opposite side of things, if you're evaluating from right to left, if we were to say O sub -10:-6, then we're starting with -10 and working backwards up to but not including -6. So in this case, O sub -10-6 would be CBT and then space. That would be our resulting substring. Final thing I want to say about this before I demo it is that you can just leave blank one side of the colon. So if we were to define O in this case, not ST, 2:blank, then that's going to start here at the T and grab everything else in the string. Same thing if you're working in the other direction. :4 would start with N and work backwards this way. Let's work for a moment with strings, substrings, and slicing. I'm going to create a name called corp. That is just like our examples actually, CBT nuggets. Now of course a capital C has a different Unicode code point than a lowercase c. So note that case is significant. If we wanted to view, work with, or extract a subset of this data, we can assign it to a name, or because we're in the interactive interpreter, we can just go ahead now and start assigning or referencing offsets. We're going to provide the root name here, square brackets, and then some substring definition. So as the example we gave previously showed, if we start at index offset 6, which is the first lowercase g, and then proceed to 10 but not including the 10th character, which is S, we get gget. What if we wanted to retrieve just the CBT? What would we do then? Well, we have to remember that the position starts at 0, not 1. This is one of those things that folks who are new to programming take a little while to adjust to. We start our numbers at 0, and then up to including 3, right? Of course, again, we have to make sure our syntax is correct. Note that I can arrow up, hit enter, and then simply change my operator. To work in reverse, we can simply use negative numbers. So -10 through -7 gives us BT and space. It all depends upon what you want to extract from a given string. Finally, we can use just the open colon to, in this case, start with the 4th offset position, capital N, and take it all the way through the end of the string. A method is a specific type of function that instead of just being a standalone code module like a function is normally, a method is a function or an operation that acts on a given object. And traditionally, the way methods work in Python, and really most procedural or especially object-oriented programming languages, is that you use a dot or a period to separate an object from a method. So in this case, you're seeing some examples where we've defined a string named st, and you can invoke several methods from the Python standard library to perform actions on the given string. So for instance, if we needed for whatever reason the offset ID value of a particular character or character sequence in a string, we could type the string name, .find, and then in parentheses what we're searching for. For instance, we could search for CBT and CBT nuggets. And what we'd get back is the initial offset of the initial character that matches that find expression. You can replace parts of a substring by using st or whatever your name is, .replace. Split is pretty cool. What split does is it cuts a string at a given delimiter. So you might have a string that has spaces in it, and you could use the space as your delimiter character, and that'll actually output a list for you. And then finally we have upper and lower, which from the names I think you can tell what these methods do. Convert the given string that you put into the parentheses into either all uppercase or all lowercase. Now there are a lot more string methods than these. These are just tend to be the most popular ones that we're going to start with. Back to the drawing board. Let's type corp to make sure that that string we defined several minutes ago is still in memory. It looks like it is. We're going to try some of these methods now. So find, again, as soon as we open the parentheses, you'll notice that a very terse online help kicks in. What I tend to do, you'll notice I've done it several times, is that I will open and close the parentheses fully and then use the arrow key to back into those parens. There's nothing more annoying than a trivial error like forgetting to close a method call. So to actually use this bad boy, I'm typing corp dot, and you're going to see another neat aspect of the integrated development environment. You'll notice that a pop-up shows up that gives us all of the built-in methods that are supported based on what your name is. And our name in this case, as we know, is CBT Nuggets, and it's a string. So I can either type find, or I can look for this in the list, depending upon how I want to do it. And then in my parentheses, I tend to open and close the parentheses together so I don't leave it out. You'll pass in what you're looking for. So in this case, I was looking for UGG and Nuggets, and what we get back is the offset, saying that in position 5 in our corp name, 0, 1, 2, 3, 4, 5. There it is. UGG starts in position 5. That's all there is to the find method. Split's pretty cool too. Let's try corp.split, and in the arguments area between the parens, I'm going to quote a space. And notice what happens. It took the input, which was our original string corp, and by the way, corp is still CBT Nuggets, and it gave us, as a result, what's called a list. A list is a multi-value array that's enclosed with square brackets. And you notice we have CBT, comma, and then nuggets. Now, because we ran this corp split without a name, that list is not being captured. So what we can do is I'm just going to create slist, and now both names are preserved. I hope you're getting a feel for this immutability business now. Let's wrap up this nugget with a quick Python script that ties together what we've learned in this nugget thus far. Note that you can create a new script from the Python shell by opening up File and selecting New Window. I've already done that, so I can open the Windows menu and select my script file. Remember also when you save your script file that you must add the .py extension in order to create your association. Now what you're seeing here is a simple 6-line program that will accept keyboard input from the user. It's asking for a number, and it echoes back or prints back the data type of the number as it originally came in. That's kind of a trick question because number one, we haven't discussed the input function yet, and number two, we don't know what the result is, the default result is in terms of data type of anything that comes back from the user. Here's the deal with the input function. Anything that comes back from the input function is going to be a string. So in the second line here, this is going to come back, guaranteed. The data type is originally class equals string. Now what we do next is we take that string, create a new name, convert it to an integer. We then echo that information back to the user. Now I'm showing you a bunch of things here actually. You'll notice that we're using a function called print that we're going to formally define in the next nugget. You notice I'm also using a comma to separate what's called a string literal. This text is going to be presented exactly like that to the user, and then we could say comma and then add another element. In this case, you notice that I'm embedding calls to other functions. You're going to see how this works in runtime in just a moment. What I do then is create a name called power that takes uconv, which is our integer that we created based on the string input from the user, raise it to the power of 8. Remember, the exponentiation is done with star star, and then finally we're going to echo back UI, which was the original value given by the user, comma, which in effect creates a space between it and the next element in this print function, string literal, raised to the 8th power is, and notice that we're including a space in that string to make formatting easier, another space, and then we're going to bring in power. From idle, we can open the run menu and choose run module to convert to a runtime environment. There's our first prompt, enter a number. I put in 2. Tells us the data type is originally, and then there's the result of our type function. We transformed a new object by taking the old string data, which is still there, remember immutability, converted it to int, there it is, and then finally that original value that we grabbed, raised to the 8th power is 256. Now you might be looking at my toy code and critiquing it. Programmers are notorious for critiquing each other's code to optimize it, and you should not take that kind of feedback personally, because really the better you can get at optimizing the code, the better everyone is, the better off everyone is. Now what we're not doing in this code is capturing what if, for instance, a user were to input a float? What if a user were to put in a string? Now these are things that we can expand upon in future nuggets. with branching and condition testing. This is an extremely narrow channel. If a user puts in anything but a raw integer, the program's going to break. I can demonstrate that by using run module and putting in a float as my number. Tells us invalid literal for int with base 10. It didn't like that. You notice that we can right-click the error, select Go to File Line, and it comes back and tells us here is where the program choked. It's going to choke in the very same way if we run one final time and try to pass in a string data, either quoted or unquoted, it doesn't matter. We're going to wind up with that problem. Right-click, go to File Line, and we're choking. So the neat thing about this debugging that I'm showing you is that this is where we can now focus our attention on creating branching to test the data that comes in from the user. What kind of format do we want to convert it to? How do we handle outliers? All of that stuff is part of the software development cycle. And finally, I think this example is a good implementation of computing when you think about it, because all computing involves data input, some kind of processing, and then output. Data types, part 1 of 2. In this nugget, we looked at a very fundamental subject indeed in the Python programming language, and even more generally in any programming language. At this point, you should understand what we mean when we say that Python is a dynamically typed and yet strongly typed programming language. You should be familiar at base, at least by name, with all of the core data types that Python has to offer. We then drilled in specifically on numbers and strings, which are really our go-to foundational building blocks in creating a Python program. You should understand now the difference between a float and an int, how to create objects that convert from one format to the other. On the string side of things, you should understand single quotes, double quotes, and as we'll get into later in the course, triple quotes for multi-line strings and documentation strings. You should understand substrings and slicing strings, as well as some of the basic string methods. We're just going to keep on building what we learn and keep iterating. Again, key principle in software development, iteration, building upon what we're learning and building a larger and larger snowball of knowledge, so to speak, as we move down the hill. I hope that this has been informative for you, and I'd like to thank you for viewing.